All right. So here, this is the penultimate, right? Lecture. Next week is the last week. Just so everyone's aware. We're not really gonna, do anything formal. It's sort of just administrative wrap-up stuff. I think please check your CUNY email addresses. I think you should have course evaluations. Please complete them. We look at them. We take them seriously. We try to we reflect on the comments, we make changes. We tweak this course every semester, so we won't see responses until sometime in the summer. So, and they're anonymous, so we don't, know who says what, but we always appreciate the feedback. If you want to talk about stuff and you want to just send us an email with feedback, we love that too. We don't hold that against we live and breathe feedback, both giving and
Okay.
receiving,
Yeah.
or we try to, sometimes more successfully than others, at least speaking for myself. All right, so tonight's the last night, which is not in the textbook. So if you looked way back when, there is a chapter in the Navarro book on Bayesian analysis. This is not going to be on the final exam. However, reason why I like having this is you're going to encounter Bayesian methods in the master's program and as a data scientist. It's an increasingly popular approach. It also I think contrasts the frequentist approach that we've had. So I think this is a great moment to review, right? So the most of what we've talked about this semester, with the exception of like the classification regression trees, um, you know, is sort of based on this notion of the central limit theorem. Can't state how important that is as a concept for traditional frequentist approach statistics, right? We're making inference, whether it's regression or null hypothesis or whatever, where we are assuming it's a theorem, so it's sort of somewhat, it's kind of provable, and it's, if you took a calculus in statistics calculus course, you kind of derive that theorem. But as sample size increases, the sampling distribution is going to approximate the normal distribution, right? I don't know how many times I've said that this semester, right? So that is fundamentally how we're making inferences if we're taking the frequentist point of view. Bayesians are going to take a different point of view. They're not going to leverage the central limit theorem. And Bayesians, right? So for a frequentist, truth is the sampling distribution, right? For Bayesians, truth is the data I have, right? So frequentists say, well, I just have one sample in an infinite number of possible samples. And Bayesian say, well, I just have one sample of data. That I know that's true because I observed that. And so they're going to make inferences to say, well, how often would I observed what I observed given some other mechanism, right? And technically we're going to call that a generative function. We'll go through that. Probably best to understand it through an example. So I'm going to start with like the additional resources. So we put the Navarro book on the website because it's an OER. It's free. You can download it, and there's a chapter, and I think it's a pretty good chapter in terms of introducing Bayesian. If you're going to dig deeper, I tend to recommend John Kruski's book, or sometimes called the Puppy book. I think it's a fairly approachable introduction. It's focused largely around R, but this notion of JAGs and STAN, those are actually those are separate languages, but they're languages designed specifically to do Bayesian analysis. And we'll see why you might want a separate language. There are interfaces if you become predominantly a Python programmer. Well, you can use Python to call JAGs and STAN. So and in both R and Python, we're going to see there's going to be sort of drop-in replacement. So if we're doing a linear regression, well, there's Bayesian approaches to linear regression, and there's Bayesian approaches to logistic regression. So the inputs and outputs look the same, but how they estimate the parameters is going to be different. Kresge's got a whole bunch of videos on his YouTube channel, so that's another great place if you prefer videos. Now, if you're looking for a nice summer read, this is not really, I wouldn't, it's not going to teach you a lot, although Sharon McGrain's, I think, gives a good explanation of what Bayes' rule is in Bayesian analysis. But it's more of like, I would consider it more of a history book. I love this book a lot because it kind of goes all the way back from Bayes in the late 1800s And Bayesian analysis was used throughout history in multiple ways. Like probably one of the more famous uses was Alan Turing, in the way he broke the Enigma, or created the Enigma machine that broke the Germans' encryption during World War II, used Bayesian methods to do that. And sort of, we're going to talk about this notion of priors and posteriors, but one of the fundamental pieces of Bayesian analysis is that you're gonna define these priors, and the priors are sort of created or can be described using prior information or prior research. And so, if you don't know anything about how in World War II this was a big deal, the Germans were changing their encryption codes every day, but they were able to decipher patterns and how they change things. And so being able to try every combination to crack the code every day would not be possible. So by learning these patterns, he could reduce the search space of which ones he would have to try through his machine he created, right? So there are a lot of interesting, right? And so it was used a lot in sort of applied areas, and really didn't catch on in the academic world or taken serious by academic statisticians until like the late 1980s, 1990s. And as we're going to see, one of the there's a lot of reasons, but one of the reasons is just the readily available high speed computers. As we're going to see, solving a lot of these problems are going to be more computationally intensive than sort of the frequentist approach. Okay. The first example I'm going to go through is actually borrowed heavily or stolen from Rasmus Bath. So he has a 3-part series. I actually did a workshop with him many years ago. It was one of the first introductions to Bayesian analysis that, at least for myself, really clicked. And then there's another piece in this later. I'm going to show you a Shiny app I've written to kind of solve the problem Bayes posed in his first paper on Bayesian analysis. So we'll look at that. Now, back in the probability chapter, there is a little bit of Bayes in the textbook, and we kind of present this theorem this way from sort of a probability point of view. And really, it's about solving the probability of A given B when you know a whole bunch of other conditions, right? So the example we can go through here is, right, so we want to know about, the likelihoods of having breast cancer, but there's a couple of different conditions we need to think about, right? So we have the sensitivity or the accuracy of breast cancer detection. And then we also have to take into account the prevalence of breast cancer sort of in the population, right? And so we could set that up in this 2x2 table, right? So, nationally, we kind of have pretty good estimates that about 1% of women have breast cancer. And then we kind of have this information about mammograms. And so we have 80% of mammogram tests that are positive are going to catch it. Like if you have cancer, 80% of them are going to catch it, but 20% might miss it. Okay. Right. So you have this test positive and test negative, right? And so if you have cancer, you have 80-20, but then if you don't have cancer, right? So you can have a positive test, right? So you could have a false positive, but then you can also have a negative, right? And in sort of this mimics what we talked about last week, predictive modeling, and it sort of mimics the type 1, type 2 error rates, right? But we can't just sum up that column because then we have more than 100%. But the question we might want to ask is, suppose you have a positive test, what are the chances you have cancer, right? So what we're saying here, what we want to solve is, what's the probability of having cancer given a positive test, right? And so that's the problem we want to solve. And so, we're going to boil this down, and you can go through the arithmetic. And if you do all the arithmetic, right? So if you have a positive test, the actual chance of having cancer is like 7.8%, right? So it's not, 80% as you might have thought, right? So that's kind of where Bayesian starts from. Now, it really comes down to true positives versus any positive results. And so if we consider it from that situation, we can kind of simplify the formula. So we can remove some components. Um, and when we think about this from a modeling or inference point of view, we kind of break it down to these different components. And these are kind of the things we're going to look at, because we're not going to, we want to solve statistical models where we can, essentially have models where we can make new predictions. So we're not talking about simple events like this. So we have, so the things we know is we have some likelihood, right? And we're going to have some prior information, probability of like some positive event, and we have the marginal likelihood. And so what we want to do is define some posterior. So prior is going to be previous information, and the likelihood is what we're going to have. Okay, so let's talk through one example to see how this works. So our goal, we have a pond nearby, and our goal is to estimate how many fish are in that pond, right? And so we need to devise some strategies to do that, right? So of course we could try to catch all the fish and count them, but that's really not really practical. So we're going to have to use some kind of sampling technique. And so here, the strategy I'm going to propose is we're going to go out in our boat and we're going to catch some fish. Let's say we're going to catch 20 fish, right? I'm going to mark those fish and return them to the pond and wait enough time so the fish have an opportunity to kind of mix themselves up, right? They could swim anywhere in the pond. I'm going to go out and I'm going to catch another 20 fish. And that second, timeout, I'm going to count how many fish are marked, meaning I caught them twice, right? And that's going to be my strategy. So let's just assume that I did this, right? I went out, caught 20 fish, marked them, returned them, went back out, caught another 20 fish. And on that second time, 5 of them were marked, meaning that they were caught twice. And so from this, I'm going to try to derive a way of estimating how many fish are in the pond. Okay. Now, turns out I actually don't know how to solve this through a frequentist approach. So this is one where Bayesian is like kind of absolutely necessary. First thing I need to do is define some kind of prior distribution. And essentially when we talk about a prior, we're just talking about our initial guesses. So I'm going to make a bunch of guesses of how many fish are in the pond. Because I know nothing about counting fish in the pond, I'm going to use something that is often referred to as a naive prior distribution. Specifically, I'm going to use a uniform distribution. So I'm going to say, I'm going to make 100,000 guesses. And what I'm going to do is say, well, there's obviously at least 20 fish because I caught 20 fish. So I know there's a floor. And given I have to have a ceiling somewhere. So I think there's no more than 250 fish. Right. And so what I'm doing here is this, I'm just randomly sampling between 2 and 250, 100,000 times. Of course, I have to have replacement because I'm sampling a lot. Right. And you can see I'm going to, essentially what I'm going to do is I'm going to iterate over this vector. And in the first iteration, I'm going to guess 199 fish. Then I'm going to say, let me guess 185, then 125, 111, right? I have one that's 49. And I just plot it. So we could see the guesses I'm going to make between 220 and 250 are all roughly equal, right? Definition of uniform distribution. So I said, I'm going to make initial guesses. So what does that mean? Well, I need to define what's called a generative function. And this is why there are languages like JAGS and STAN, because it's a syntax sort of designed for defining these kinds of generative functions. Now, if you're just trying to predict things, like I said, there are built-in replacements. So in this case, this doesn't exist, right? There's no library in our package or even a Python package that's like count the fish generative function. It just doesn't, but it's easy to define. So what am I going to do, right? I just need to mimic that sampling technique I use. So I define this function called pickFish, right? And it takes one parameter, which is the number of fish that I think, sort of that number of fish is my guess of how many fish are in the pond. So the first time I call this function, I'm going to call it with 199. Okay. So if I pass 199, what am I going to do? Well, I'm going to create a vector of length, 199. Well, actually, yeah, 199. So 20 of those, I'm sorry, 179 of those are going to be 0, and 20 are going to be 1, right? So I have this vector of a length of 199, but 179 of those elements are 0, and 20 are 1s, right? That's sort of mimicking what I did when I went out on the pond to catch fish. Then all I'm going to do is randomly sample 20 from this vector called fish, right? And sum it, right? And by summing it, I'm going to get the count of how many fish were caught a second time, right? So in essence, this function just replicates what I did here, okay? So it returns, what it's going to do is return how many, well, this returns how many I have. Okay, great. So I'm going to initialize a vector called n marked. I'm going to initialize it with NA, and I'm going to n draws 100,000. So I'm also going to do 100,000 here. So I'm going to loop through this, right? And so what am I doing? Well, the first time when I is 1, right, I'm guessing 199. I'm going to call pick fish, and I'm going to save back how many were caught a second time. And then I'm going to guess 185, and I'm going to do that procedure again. So I'm going to do this 100,000 times, right? And so what's returned? So I return n marked. So I'm going to get numbers between 0 and 20, right? If I caught 20 fish on the second time, I could, so it's 20 is the max, 0 is the minimum. So when I guessed 199, I got 1 fish kind of caught the second time. When I guessed 185, I got 2. When I guessed 125, I got 5, right? So this is it, right? This is a good candidate, right? So 125, I got 5. Remember, 5 is what I observed, right? So what I want to do to this then is I'm going to take this vector and I want to keep all of the ones that are equal to 5 because that's what I actually saw. And so here I can take that, right? So n fish, remember, is how many I guess. So I'm keeping all the ones where I thought I saw 5. And so that defines my posterior distribution. And then I could just plot it. This is what my posterior distribution looks like. So we could see if I take the median, right? This red line is the median. So notice it's not normally distributed. We're making no assumptions about the shape of this distribution. It's fine that it's skewed and not normal. So a lot of times when we use Bayesian and I want to get the center, I'm not going to use the mean. I'm going to use the median because it's skewed. So I might, my best guess is to say there's probably about 100 fish in the pond, but I also added the 25th and 75th percentile. So I'm 50% sure there's somewhere between roughly 75 and 125 fish in this pond, but I'm going to guess 100. Okay. So that's how I make my inference, right? Essentially, I just generated a lot of fake data using some kind of random process to see how often I saw what I really saw when I went out in my boat on the pond. Okay. Now, this is where things get interesting with Bayesian analysis. And this is where frequentists often critique Bayesians because I could define a different prior, right? Let's say I go out to the pond and there's some fisherman out there. He's like, I am an expert on ponds and fish, and I think there's 200 fish in the pond. Okay, great. You're a so-called expert. So instead of defining a uniform prior distribution, I'm going to define here, in this case, I'm going to use a binomial distribution centered on 200, right? So I'm using the random binomial. And so this is going to be my vector of guesses, right? Instead of every value between 2 and 250 being equal to likelihood, well, I'm going to guess around 200 more. And I'm actually going to go as far out as, in this case, the ceiling is not so much of effect. I'm going to guess as far as 800, right? And as low as 0, but I'm not going to try 0 very many times. I'm going to try values around 200 more, right? See how that what's going to happen. This defines my initial guesses. So from here, everything's the same, right? All this code is exactly the same. I'm looping through, except I'm using a different prior, and then I'm keeping only the ones where I see 5 because that's still my truth, right? And so now I have a different posterior distribution. Now here, my median is a little bit higher than 100, but note that my 50% interval doesn't span 200, right? And so this is where Bayesians come back, right? So, so that, there's critiques, right? So I could define a prior, such that it may make my inference be significant, where, if I used a different prior, maybe it wouldn't be. And there is some truth to that, but in my experience, a lot of these procedures are fairly robust to bad priors. And in this case, I deliberately picked 200 because that is clearly a bad prior, right? Probably closer to 100 is where it is. And you can see when I put in the 50th, you know, percentiles, um, I'm still capturing 100, right? So, but it is true, right? I could have picked if I went a little bit higher than 200, maybe I wouldn't have spanned 100 and maybe not captured it. Okay. So far, so good. So that's, you know, um, in essence, right, if we kind of apply this back to what Alan Turing was doing, right? So what was his prior, right? So he had a machine where he was trying to, given some, if you know how encryption works, you have a code, right? If you have these two-way encryptions, I have a code to encode something, and then I need a code to then unencode it, right? So there's a potentially infinite number of codes that you could try to decrypt something. And so what Alan Turing was able to do is say, well, we know, at some point maybe they figured, well, we know, I don't know this for sure. It's been a while since I've read that book, but like, um, okay, we know the code is 16 digits, right? So that's a bit of prior information that could define your prior distribution for the codes that you're going to try to guess to break the encryption. Right. So if I know that, I should leverage that. Right. That's what Bayesians are saying. We know this is true. Right. In terms of like in randomized control trials. Right. So like take Angela and we're doing a randomized control trial on DAX. Now, we're using frequentist approaches because in our reports, um, we try Bayesian methods sometimes in predictive models, but in terms of reporting inferences, Bayesian hasn't really caught it on, I think, in the educational journals. But we could do that, right? We could say, well, there's prior research on the effectiveness of these types of educational things. So instead of just assuming zero, right, the frequentists are always centered, using a null hypothesis, right? We're always inferring against the null, right? And Bayesians are going to say, well, that's crazy. We know from prior research the null is not true. So instead, we should say, well, we think the effect size is going to be 0.1. So let's test it to see if it's around 0.1. But the data we have collected is truth. We know that's true, right? And so that's kind of their argument. So when we think about like if you're going to do a regression model, so you can look up a Bayesian logistic regression, and you're just going to change the function name, right? In the same way we went from LM to GLM. A lot of this stuff is the same. We just change function names, but the way things are going to be estimated is a little bit differently. So in Bayesian approaches, right, we're not minimizing some squared residuals. We're not maximizing a likelihood if we're using a generalized linear model. Instead, it's going to estimate parameters based upon prior. And if you just do anything, it's actually going to use a uniform or naive prior, right? It's all guesses. And it's going to keep trying to estimate parameters until it comes close to what you actually see in your data, right? Instead of the kind of the other way. So the other example I want to talk about real quick. So this is actually from Bayes' first paper. And you got to realize late 1800s and early 1900s, statisticians were sort of obsessed with games, right? And kind of still are. Like a lot of the stats courses I take are about understanding the probability of games, right? And we do that. We've talked about Vegas games and card games, but sometimes they make up silly games. So Bayes invented this game, and he said, well, let's assume a pool table has a length 1. And I'm going to throw the 8 ball on the pool table, but I'm not going to tell you where the 8 ball is. The goal is for you to tell me where the 8 ball is on the table. All I'm going to tell you is I'm going to throw subsequent balls, and all I'm going to tell you is whether or not the ball lands to the left of the 8 ball are to the right of the 8-ball. And with that information, you need to tell me where the 8-ball is. So we have this little shiny app that we can actually do this. Okay. So first thing is and if I can go to a histogram, I just want to show there's some random noise here, but I'm starting with a uniform distribution. So over here on the right is my prior, right? The 8-ball can be literally anywhere on the pool table when we start. I don't know. Okay. But what I do know is Dr. Bayes throw the ball and tells me, okay, the ball I just threw landed to the left of the 8-ball. All right. So what I'm going to do is take all of these guesses and generate a random number. So if let's say I'm at 0.25. So 0.25 is my guess. I think I'm going to, for the moment, assume the 8-ball's at position 0.25. I'm going to draw a random number between 0 and 100. If the number is greater than that, I'm going to keep it. If it's less than that, I'm going to ignore it, right? Essentially, right? If you think about it, if the ball landed to the left, then the likelihood of the 8-ball intuitively should hopefully make sense that the 8-ball is probably more likely to be on the right side of the table just after this one. It doesn't have to be, right? Because there's random chance. So, but I go through that, all of those guesses, and I end up with this posterior distribution, right? Given that one bit of information, the 8-ball's probably towards the right side of the table, right? And up here in the upper right-hand corner, this is going to be the median of that distribution. And here you can adjust. I have a 50% confidence range, right? Okay, great. But let me throw another ball. This time it landed to the right. Okay. But I'm not going to start at 0. What I'm going to do is take my posterior from the first iteration. That becomes my prior in the second iteration. And so I'm going to go through doing all that guess. But now I'm doing the opposite because the ball landed to the right. Right. So you can see my posterior now kind of shifted. Now it's a little bit more symmetrical. So I can do this again. Now we landed to the right, then to the right, now to the left, right? I could do this a few times, right, left. But in essence, right, after each iteration, this posterior becomes this prior. I do my generative function a bunch of times, right? I get this posterior. This posterior becomes this prior, and I'm just kind of zigzagging here up, all right? And so, and you can see each time I'm updating my guess. So after 7 iterations, I'm guessing that the 8-ball is just left of center, right? And if you want to do this, some more times, you can do this again. If I refresh the app, it'll pick a new place for the 8-ball, but you can always click this button and we can actually see here's where the 8-ball was actually at position 0.5. It was kind of in the center, right? And so you could here was it the first ball thrown, the second, third, fourth, fifth, right? And you could do this over and over. But what's kind of remarkable, right, is we had it kind of early, and then, but after 7 iterations, we're kind of there, and we can, do this over and over, and you can start over, right? So, right, and you can kind of play it through if you want to see the pool table as you go. When it's over there, might take a while before we get that one on the left. So sometimes things can go awry, right? It's kind of unusual that all these balls are over on the right-hand side. But if we get one that lands to the left, I think it'll correct itself. Wow. So every so often you get weird random things, right? That's randomness for you. So anyways, again, this is a problem I don't know how to solve using a frequentist approach. So Bayesian can be kind of useful in those contexts. So right, this is just really short. This is really meant to kind of whet your appetite. It's sort of a bonus topic. It's not in the textbook, but I think it's really important because you're going to encounter Bayesians. Oh, and I don't know, for those in New York City, I think I mentioned this. Angela and I think are both going to be, I don't want New York Times, New York, our conference. So I think I told everyone about this. Next Thursday and Friday is going to be our conference in New York City. and one of Andrew Gelman, I think, who is one of the top Bayesian researchers. He's from Columbia University. Will give a talk there. But there's also some other great speakers. Hadley Wickham's going to be speaking there, among other people. So if you go, let us know and say hi, because we'll be there. So I threw the 1 minute. I didn't throw the 1 minute paper link in there. Let me do that real quick. Happy to answer questions. Otherwise, at this stage, check Blackboard, make sure, if you had any missing assignments, get them in. First presentation start at noon tomorrow. So we got 2 sessions tomorrow, 2 on Monday and 2 on Tuesday. We'll meet briefly next Wednesday at this time. Final exam will be available right around the start of the meetup, so you can take a peek and ask questions if you have it. Final exams due Monday on the 19th, midnight on the 19th. But otherwise, we're in the home stretch here. Any questions?
Jason,
Yes.
could you just maybe explain how the name posterior came about?
Oh, I don't know I don't know who first coined the word posterior, but the notion is that it's on the backside, right?
The backside of what?
Of the generative function, right? So, um,
Oh, I see. Okay.
so if a prior is defining the distribution of my initial guesses. So I'm going to run
Hmm.
that through what we call a generative function, a whole bunch of times to generate a new data set, right? And so on the back end of doing that, generating that fake data, so that's the backside. So somebody coined it the posterior distribution. Let's consult Google, I guess. I could ask ChatGPT, but I might just make up a guess. Who coined the term posterior distribution? Uh, huh. I don't. So this would be too late. Um, yeah, it doesn't. If Wikipedia doesn't say, I don't know where. Um, yeah, I don't know who coined the term. That's a good question.
Okay.
It might be in that book, The Theory That Would Not Die. Oh, look at that. Here's a John Kruski.
It just comes across as a kind of a strange name.
Yeah, it's probably well, it's been around for a very long time, even though it's only gained popularity in the last couple of decades. Um, so I never thought of it that way, but yeah, it is a bit of a strange name.
Okay. All right. Thank you.
But yeah, um, so I think Bayes was English, um, so it's probably this. I think this work was a lot happening at like Oxford University and Temple University, kind of in the UK. So then if I see Andrew Gelman next week, maybe I'll ask him. If anybody's going to know, he might know.
Mm.
He's also have to have right here. This is considered but Andrew Gelman and a bunch of others. This is considered the Bible on Bayesian analysis, but it is
What's the title of that book?
Bayesian data analysis. It's in its
Oh,
third
okay.
edition. It is extremely dense and technical. It gets pretty deep pretty quick. So I think John Kruski's is a better place to start. I think his writing's much more approachable. It's technical enough, but not overly technical. Like, it, you know, the, by page 8, I don't know if you can see this. Like the number of formulas is insane. Where Kresge tries to describe stuff and then, sort of through pictures and things like that. Oh, somebody's asking, will the presentations be proctored? Yeah, Angela and I will be there if that's what you mean. So we'll kind of play MC. And if you do slidey is great. Whatever, you can use PowerPoint, Keynote, slidey, IO slides, whatever you want to use. If you could try to create a PDF of your slides and post those on Blackboard. In 10 minutes, you have 10 minutes. So, all right, we look forward to it. This is fun for us. All right, well, let's call it a night. Good luck, everyone. We'll see everyone at some point in the next week.
Yep. Yeah. Be sure to just go through the rubric if you haven't already to make sure all the parts and the components that we asked for are included in your presentation.
We have a rubric and a checklist for you. So, all right. Have a good night, everyone.
Good night.
Thanks.